Well, I'm going to start out by numbering them or lettering them A, B, and C again so I can refer to them quickly. And I'm going to go ahead and I'm going to use the elimination or the addition method. And to do that, I'm going to eliminate the y variable because I look through here and I see that it's just a positive 1y or just a positive y in every equation. So I'm going to combine -1 times equation A with equation B first. So -1 times equation A, I'm just going to multiply every piece by -1, would be -x, -y, -2z equals -9. That's just -1 times x is -x, -1 times y is -y, -1 times 2z is the -2z, and -1 times 9 is the -9. Equation B is just 2x plus y minus z equals 2. And we'll combine those equations. -x plus 2x is positive 1x. -y and positive 1y cancel out, gives us 0. -2z and -z make -3z equals -9 plus 2 is -7. So there is our first two variable equation, x minus 3z equals -7. Now I haven't used equation C yet, so we need to use equation C. I'm going to combine equation C with that same -1 times equation A. So -1 times equation A from up above here is -x, -y, minus 2z equals -9. Equation C, x plus y minus 3z equals -6. And now we'll combine those two equations. Well, something weird happens here. X and -x cancel out. -y and y cancel out. -2z and -3z make -5z. -9 and -6 make -15. There is our second equation for our two-equation, two-variable system. Now it's relatively simple from here because when we do our two-variable, two-equation system, we have x minus 3z equals -7. It's from this top one. And then we have -5z equals -15 from this bottom one. And to solve this system, we've already got one equation that only has one variable in it. So I'm going to solve that one for z. Dividing by -5, z equals -15 divided by -5 is 3. So z equals 3. I substitute that back in to find x. The only equation that has x in it out of those two is the top one, so we're going to use that one. So putting that in, x minus 3z becomes 3 times 3 equals -7. Three times 3 is 9, so that's x minus 9 equals -7. We'll solve for x by adding 9. X equals 2. Now we go back up to one of the original equations to find y. I'll just use the top one. So x is 2 plus y plus 2z becomes 2 times 3 equals 9. 2 times 3 is 6. So 2 plus y plus 6 equals 9. We continue to combine. 2 and 6 makes 8, so y plus 8 equals 9. And finally, we solve for y by subtracting 8. y equals 1. So our ordered triple here, trio, x is 2, y is 1, z is 3. Any questions on that? All right. Did you guys have any questions from the homework in my math lab that you'd like me to go over? Okay, good. The new material for today is we're going to talk about matrices. What a matrix is simply an organized set of numbers. Just like the ordered pair in an equation, the location of the number in the matrix tells us what it stands for. Most matrices, and actually a matrix can be more than numbers. If we're dealing with other topics, it can be a set of anything really. In computer programming, you have matrices, or they're called arrays, where you have almost anything in them. Of course, being math class, we're only going to deal with numbers. These square brackets indicate that what's inside of it makes up a matrix. So there's a matrix. This matrix has elements in it. In fact, it has 6 elements in it. Each entry in the matrix is an element. Now, I chose to make these all single-digit numbers, but they could be as big a numbers as you wanted. 3, 4, 5 digits, however large they needed to be. I'm going to use single-digit numbers because they're going to be easy for us to calculate with as we go through these examples. A matrix has rows. The rows go horizontally. That would be row 1, that would be row 2. This matrix has 2 rows. A matrix has columns. So we column 1, column 2, and column 3. This matrix has 3 columns. If I want to find the position in a matrix, I might have row 2, column 1, or often we'll list it using just an ordered pair like that. The item in the element in position 2, 1, that's row 2, column 1. What number would that be in that position 2, 1?
4.
The 4. Very good. So 4 is the number in that position. Dimensions. The dimensions of a matrix are quite simply listed as the row by column. Now that doesn't mean we're actually multiplying them out. We're just going to list this dimension up here as a dimension of 2 by 3. 2 rows, 3 columns. We have special matrices called square matrices or square matrix. In a square matrix, the number of rows equals the number of columns. So a square matrix might look like that. That would be a 2 by 2 square matrix. This, of course, would be a 3 by 3 square matrix. If you remember back to doing ratios and proportions, in proportions there are all sorts of things you can do that doesn't change the relationship between the variables, basically. If you had that proportion A over B equals C over D, one thing you could do is you could flip them both over. B over A is still going to equal D over C. You could switch numbers diagonally. If you switch the A and B, or the B and C, they're diagonal. A over C equals B over D is still going to be true. And you could switch the other diagonals. D over B will still equal C over A. We have similar things in matrices that we are allowed to do. They're referred to as elementary row operations. We choose to do these operations with a row just because it's easier for us to think in rows. We could very well do these same operations with columns. We just have to make sure we only did them with columns. And when we do them with rows, we're only going to do them with rows. So to switch over, if you were going to use columns, you'd only be able to manipulate columns. You'd have to leave all the rows alone. But for elementary row operations, things that you are allowed to do is you can swap any two rows. What does that mean? Well, in this matrix up here, if I call them rows 1, 2, and 3, I could swap two of those rows. Let's say I want to swap rows 1 and 3. I get that. That is an equivalent matrix. How do we judge equivalence? Well, we'll talk about that later on if there's time. That is an allowed row operation. It's to swap any two rows. Just like we could with our systems of equations, we could multiply or divide every element in a row by the same number. So what would that mean? Well, that means we could go up to a matrix like this. We could pick a row. Let's pick the second row. Let's multiply every element in it by 4. So that's going to give us this matrix. The top row stays the same. The second row is multiplied by 4. So 4 times negative 2 is negative 8. 4 times 5 is 20. 4 times 0 is still 0. And of course, the bottom row still stays the same. The third operation is a little bit more confusing, but it's very important for doing some of the operations with a matrix. We can add the elements from one row to the corresponding elements in another row. So the first row, the one that we're going to add to the other one, it's still going to stay where it is, but we're going to also add it to another row. So let's say I want to add row 1 to row 2. So what that means is row 1 is still going to be the same here. It's still going to be 11, -1, 15. It still stays there. We're not doing anything with row 2, so that's going to stay as -8, 20, and 0. But I'm going to add all the elements in row 1 to row 3, and I'm going to put them in there. So 7 gets the 11 from row 1 added to it. That makes 18. 13 gets the -1 from the first row added to it to make 12. -8 gets the 15 from row 1 added to it to make 7. That's an equivalent matrix. Well, why is this important to us? Well, because if we combine this concept with something called an augmented matrix, an augmented matrix is a matrix that has additional numbers attached to it. Okay, so an augmented matrix, we take that regular matrix, and usually it's a square matrix. So I'm going to have 4, 3, -1, 5, 1, 2, 0, 4, 2, and we're going to attach numbers, extra numbers to each row. And to show which ones are attached, there's usually a break line like this, and on the other side are the augmented numbers. That's an augmented matrix. The reason an augmented matrix can be useful to us is we can use an augmented matrix to represent one of our systems of equations. Let's take a system like 2x plus 3y plus 6z equals 3. 3x plus 4y minus 5z equals 2. 4x minus 2y minus 2z equals 1. There's a system of equations. We can use an augmented matrix to represent this. To do that, we first have to have everything lined up. This is all of our x values right here. We have all our y values right here. All of our z values are right here lined up. Our equal sign is there. And then, of course, all of our constants are on the other side of that equal sign. Our augmentation line, that break line, ends up being where the equal sign is. So when I enter this into my matrix, I have my x value, which is the x coefficient, which is 2, y coefficient, which is 3, the z coefficient, which is 6, my break line, then my constant, the 3. The next line, the next row, I have 3 for the x coefficient, 4 for the y, -5 for the z. On the other side of the augmented line is 2. Last row will be 4, -2 for the coefficient of y, also -2 for the coefficient of z. Then on the other side of my augmented line, my break line, is 1. There's my augmented matrix to represent this system of equations. Any questions on where this matrix came from, how I got the numbers put into it? Okay. That's our starting point. The rest is where it starts to get difficult. We're going to use our elementary row operations to change this matrix into something called a diagonal matrix. A diagonal matrix is a matrix that only has values along the diagonal. Everything else in it is 0. Well, it's more useful to us if it's a unit diagonal matrix, which means along the diagonal, they're all 1s. Now you'll notice I only did a 3 by 3 illustration here, because over here in this augmented matrix, the matrix really is those 9 numbers are the 3 by 3. This part over here is an augmentation. It's going to go with those numbers. We're going to use it with those numbers, but it's an extra piece to the matrix. It's not technically part of the matrix itself. These numbers are the matrix we're going to work with. But whatever we do to a number, we have to do with the augmented piece of that row as well. So we're going to do this kind of like what we would do elimination. Actually, it's exactly like we do with that addition or elimination. We try to find values so that when we add rows together, they will cancel out. Well, right now, that's not going to happen. Nothing is going to cancel out. So what I want to do is I want to try to make values start to cancel out. And one thing I would notice, there's a lot of different possibilities here. One thing I notice is if I multiply this bottom row by 2, I'm going to get a negative 4 here. I can combine that with a positive 4 there to make that a 0. Let me show you what I mean. Remember, that's one of the things we're allowed to do is multiply a whole row by the same number. So my top row doesn't change. My second row doesn't change. My third row gets multiplied by 2. 2 times 4 is 8. 2 times negative 2 is negative 4. 2 times negative 2 is also negative 4. And even though that's not technically part of the matrix, I have to do the same thing to the augmented piece. 2 times the 1 is 2. Now I'm going to replace the bottom row by adding the second row to it. I'm going to start writing just a little bit smaller just so that I can keep both matrices on the screen at the same time. So my top row doesn't change. My second row isn't going to change. But my bottom row is going to change because I'm going to add the second row to it. So 3 plus 8 makes 11. 4 plus negative 4 makes 0. That's one of the things we wanted to do. Negative 5 plus negative 4 makes negative 9. 2 plus 2 is 4. So we have managed to get one of the zeros we were looking for our diagonal matrix. Typically, it's best if we ignore this one. We've got a 0 in this row. It's best usually if in the next step we ignore that row and work with the other 2 and try to get a 0 in the same position in one of the other 2 matrices. Now, I don't want a 0 in that position in this matrix because that's the spot where I need a number. So what I want to try to do is I'm going to try to get a 0 in that position of the top row. So I'm going to combine the rows 1 and 2 to try to make a 0. To do that, I'm going to have to multiply them. I'm going to multiply the top one here by a negative 4, and the second row here by a 3. So my top row, negative 4 times 2 is negative 8. Negative 4 times 3 is negative 12. Negative 4 times 6 is negative 24. I have to do negative 4 times 3 is also negative 12. My second row, I'm going to multiply by the 3. 3 times 3 is 9. 3 times 4 is 12. 3 times negative 5 is a negative 15. 3 times 2 is 6. My bottom row, my third row, is staying the same. I haven't done anything with it. Now in my next step, I'm going to add that second row to the top row. So 9 plus negative 8 is 1. 12 plus negative 12 is 0. We wanted a 0 there, so that's good. Negative 15 plus negative 24 is a negative 39. That's a little ugly. And 6 plus negative 12 is negative 6. Of course, the second row is going to stay the same. Now to simplify life on us here, I'm going to reverse one of the things I did. I had multiplied this row by 3 just a little while ago. I'm going to divide by 3 to simplify that row a bit. So my top row and my bottom row aren't going to change here. Dividing by 3, 9 divided by 3 is 3. 12 divided by 3 is 4. Negative 15 divided by 3 is negative 5. 6 divided by 3 is 2. I've just made that middle row a little less ugly. Well, I still need to get zeros here, 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 and here. So I have to figure out ways to eliminate those values. Well, to eliminate, let's look at the 39 for right now. Actually, let's look at the 11 first. Let's try to get rid of that 11. I don't want to use the middle row because the middle row has a value here. And that would give me a value here. So what I want to do is I want to use that top row, because that top row has a 0 there, so that'll keep a 0 in that position. To make the 11 go away, I'm going to take the top row and multiply it by negative 11. So it's going to cancel that 11. So that top row negative 11 times 1 is negative 11. Negative 11 times 0 is 0. Negative 11 times negative 39 is 429, yes. And negative 11 times negative 6 is a positive 66. My other rows do not change. Now I'm going to add that top row to the bottom row. I'm going to combine something here. Right now I'm going to leave the top row blank. I fill in the second row hasn't changed. 3, 4, negative 5, and 2. The bottom row, negative 11 plus 11 is 0. 0 plus 0 is 0. 429 plus negative 9 is 420. 66 plus 4 is 70. Before I rewrite that top row, I'm going to undo what I just did to it. I just multiplied by negative 11. I'm going to divide that negative 11 back out. So that's going to be 1, 0, Oh, what was that? Negative 39 and negative 6. So I did 2 steps all at once there just to save myself a little space. In my bottom row right now, I am so close to being done. I want this to be a 1 and not a 420. So I'm going to divide that row by 420. So my top rows will stay the same. Zero divided by 420 is just 0. 0 divided by 420 is 0 again. 420 divided by 420 is 1. 70 divided by 420 is 1/6. Next, now that this bottom row only has a value in that last place, I can use it to get rid of the values in that last place, that third column of the other 2 rows. So that's what we're going to do. Let's get rid of this negative 5 here first. To get rid of that negative 5, I would have to multiply this by a positive 5. So my top row doesn't change. Second row doesn't change. Third row is multiplied by 5. 5 times 0 is 0 in both cases. 5 times 1 is 5. 5 times 1/6 is 5/6. Now I'm going to add that third row to that middle row. So my top row hasn't been changed. That second row, 0 plus 3 is 3. 0 plus 4 is 4. 5 plus negative 5 is 0. 5/6 plus 2 is 2 and 5/6. My bottom row, before I rewrite it, I'm going to divide out that 5 that I just multiplied by. So it goes back to being 0, 0, 1, and 1/6. While I'm at it, let's get rid of that negative 39 in the top row. To make that go away, I'm going to multiply this bottom row by a positive 39. So my top row is unchanged. Second row is unchanged. My bottom row times 39, 39 times 0 is 0. 39 times another 0 is 0. 39 times 1 is 39. 39 times 1/6 is 6.5. Now I'm going to add the third row to the first row. So 0 plus 1 is 1. 0 plus 0 is just 0. 39 plus negative 39 is 0. 6.5 plus negative 6 is just 1/2. The middle row is unchanged. That's 3, 4, 0, and 2 and 5/6. That third row, before I write it down, I'm going to undo what I just did. I'm going to divide by that 39 to get it back to what it was. So it goes back to 0, 0, 1, and 1/6. We're really close here. We have zeros in 4 of the spots we wanted them. Actually, in 5 of the spots we wanted them. We need to get a 0 there. To get rid of that 3, I'm going to use the top row because there's a 1 in that position. And there's zeros every place else, so it won't change anything else on us. So to do it, I'm going to multiply that top row by a -3, so it'll cancel out the 3. -3 times 1 is -3. -3 times 0 is 0 both times. -3 times 1/2 is -1.5. And of course the other 2 rows do not change. Now I'm going to add that top row to the second row. Now in this next matrix, I'm going to leave that top row blank for a minute. Because I'm going to divide that 3 back out before I'm done. But -3 plus 3 in the middle row will be 0. 0 plus 4 is still 4. 0 plus 0 is still 0. Now this should have been a -1/2 over here. 3 times 1/2, or -3 times 1/2 is a -1.5. So -1.5 plus 2 5/6 is 1 1/3. Before I rewrite that top row, I'm going to divide back out that -3. So I'll be back to 1 0 0 1/2. My bottom row hasn't changed. 0 0 1 1/6. We're almost there. The only thing that's left, I've got zeros in all the right places. I have 1s here and here. I need to make that a 1. To make that a 1, I need to divide that row by 4. So my top row doesn't change. My middle row, second row, 0 divided by 4 is 0. 4 divided by 4 is 1. 0 divided by 4 is 0. 1 1/3 divided by 4 is 1/3. And my bottom row does not change. 0 0 1 and 1/6. Now we've created that diagonal unit matrix that we wanted here. This gives us the solution to that system that we started with. Remember that system of equations we had about 4 pages up? This is in the x position, so that's saying that x equals, its augmentation is 1/2. This one is in the y position, that's saying 1 equals, the augmentation of that row is 1/3. And this one is in the z position. That's saying z equals, the augmentation of that row is 1/6. So the solution to that system of equations is the ordered triplet 1/2, 1/3, 1/6. Loads of fun?
I don't know about that.
I know putting the fractions in there is kind of cruel, but I'm not a huge fan of using elementary row operations to solve systems of equations. This textbook chooses to use that as the matrix method of solving systems. As you can see,
Yeah, it's a lot of work.
it's a lot of work. Now, there are shortcuts. You can, I mean, even here, I combined steps a couple times. I added the top row to the bottom row to cancel out the 11s, and then I divided the top row all in the same step. And there, you can make it even shorter yet if you get good at it. But even I'm relatively good at math, if you haven't noticed. If I try to combine too many steps at once and shorten up this process, I end up making mistakes. I get answers that don't make any sense. So I was very meticulous here to go step by step. In the few spots I combined two steps is where I had to divide back out what I had just multiplied by. Even with combining that, it took up a lot of paper and it's a lot of work. Why are these row operations and augmented matrices important? Well, matrices is the way a computer thinks. So if you're into computer programming and numerical arrays in computers, these same rules apply to most numerical data arrays. And you can do the same things in those data arrays. This is one of the methods that computers will employ to solve systems of equations. There is, however, in fact, if you have the graphing calculator, as I do here, you can use that graphing calculator. Let's go back up here to the original system of equations. This is our original matrix, augmented matrix that we had started with. I can put that in my graphing calculator. Where's my matrix function? There it is. I can do second matrix and go to edit and just select any one of them to edit. This is a 3 by 4 if you include the fourth column for augmenting it. Enter a 3 by 4 matrix and I can enter it in. 2, 3, 6, 3. 3, 4, negative 5, 2. 4, negative 2, negative 2, and 1. And I can make the calculators programmed to do these row operations to create that diagonal unit matrix. The command for it, if you go to matrix, the math menu is RREF. REF stands for row echelon form. That's just diagonal with any numbers on that diagonal. RREF stands for reduced row echelon form. RREF. If I select that, I still have to select which matrix, so I go into my matrix menu and I select matrix A. Notice it produces a matrix that's exactly what we just got, only it uses decimals instead of fractions. So X is 0.5 or 1/2, Y is 0.33333 or 1/3, Z is 0.16666 or 1/6. So using this, if you have the electronics already programmed to do the operations, you can find the system of that solution very quickly. If you have a graphing calculator, you're more than welcome to use it on these. If you don't, I don't really recommend you go out and buy one. They're $120, not worth the 3 or 4 days that we're going to be doing this. But those row operations is the method that the textbook uses to solve systems of equations. To me, there's an easier way of doing it, and I'm going to show you that right now. Well, before we get to it, I would go a little bit of background information. There's something called a determinant. A determinant is a single number that can be used to summarize a matrix. So I have this matrix here. This is and it can only be done with square matrices. So this is a 2 by 2 square matrix. The determinant of a 2 by 2 is found by taking the down diagonal product, or downward diagonal product, in this case that's 12, the up or upward diagonal product, in this case that's 2 times 5 or 10, and you subtract the upward minus the downward. So 12 minus 10 gives you 2. Two is what is referred to as the determinant of that matrix. 2 by 2 matrix, relatively simple, down product, up product. If it's a 3 by 3 matrix, a little more complex. See, let's do a different number here. Let's do 2, 3, 6, 3, 4, negative 5, and 4, negative 2, negative 2. If I just do a single down diagonal and a single up diagonal, I'm going to miss almost half the numbers in this matrix. So what happens is the down diagonals, there's actually 3 of them. There's a down diagonal for every element in the top row. So this is the first one right here. 2 times 4 times negative 2 is a negative 16. The second one starts with this second element of the top row. 3 times negative 5, well, in order to finish that off, it has to wrap around and pick up the 4 at the beginning of the third row. Well, to make that a little easier on us, I usually rewrite those first 2 columns. So that first column, 2, 3, 4, I'm going to write it at the end here. Then I do the second column. The 3, 4, negative 2, I write that after the repeat of the first. So now instead of having to go from here and wrap back around to the other side, I can just keep going right down. So that's 3 times negative 5 is negative 15, times 4 is negative 60. That first one was a negative 16, by the way. 2 times 4 times negative 2 was negative 16. 6 times 3 is 18, times negative 2 is a negative 36. So my down diagonal products now get added together to make the sum of my down diagonal products. So I got negative 16 and negative 6 is negative 76. Negative 36 is a negative 112. Now I do my up diagonal products. Start with the first element of the bottom row. 4 times 4 is 16. Times 6 is 96. I start with the second element of the bottom row. Negative 2 times negative 5 is positive 10. Times 2 is positive 20. Then I start with the third element of the bottom row. Negative 2 times 3 is negative 6. Times 3 is negative 18. And we'll add those all together. 96 plus 20 is 116, plus negative 18 is 98. Just like with the 2 by 2s, we take the up number minus the down number. So negative 112, even though it's on, or sorry, we don't take the up number. We take the down number minus the up number. So the negative 12 minus 98 is negative 210. That's the determinant of that matrix. So how does this make life easier for us? Well, let's go back to that system of equations we were looking at. 2x plus 3y plus 6z equals 3. 3x plus 4y minus 5z equals 2. 4x minus 2y minus 2z equals 1. There's something called Kramer's Rule. Kramer's Rule is telling us that we can create matrices from this system of equations. Find the determinants of those matrices and use those determinants to find the solution. Kramer, first of all, just like we had to with the augmented matrix, we have to line them up x's, y's, z's equals constants. We still got to line them up like that. They're already done for this system. Kramer defines something called a base matrix. He labels the base matrix M. That base matrix is the x coefficients, so 2, 3, and 4 in the first column. The y coefficients, 3, 4, and negative 2 in the second column. And in the third column is the z coefficients, 6, negative 5, and negative 2. You'll notice, by the way, instead of putting the square brackets around this, I just put straight lines. Those straight lines means find the determinant. So that's telling us that this is a matrix, but we're going to be finding the determinant of it. Now, if you're paying close attention, you'll realize that's the same matrix I just gave you up here. We just found its determinant to be negative 210. Kramer defines something called the X matrix, abbreviated with a capital M with a subscript X by it. In the X matrix, it's named the X matrix because the X variables, the X coefficients, are replaced. They're gone. They're not in this matrix. Where the X coefficients would have been, like they were up here, we're going to put in the constants. So that's going to be 3, 2, 1 in that first column. The next two columns are the same. We have the y coefficients, 3, 4, and negative 2. And the z coefficients, still going to be 6, negative 5, and negative 2. You might notice that once again, I put the straight lines there, which means we're going to find the determinant of this. Why did I write 3, 2, 1 there? I'm repeating that first column. Right next to it, I'm going to write the second column again of 3, 4, negative 2. So on our down diagonals, first element gives us 3, 4, negative 2, which is 3 times 4 is 12, times negative 2 is negative 24. Next, second element, 3 times negative 5 times 1, negative 15. Next element, 6 times 2 times negative 2 is again negative 24. Adding those all up gives us negative 63. On the up diagonals, 1, 4, and 6 is 24. The second up diagonal, negative 2 times negative 5 is 10, times 3 is 30. That's a positive 30. The next up diagonal, negative 2 times 2 is negative 4, times 3 is a negative 12. 24 plus 30 is 54, minus 12 is 42. We do the downs of negative 63 minus the ups of 42 gives us a negative 105. That is the determinant of the X matrix. Kramer's rule says that once you have the determinant of the X matrix, the X value for that system of equations is the determinant of the X matrix divided by the determinant of the base matrix. The determinant of X matrix is 105. The base or negative 105. The base matrix was negative 210. It divides out to be 1/2. Well, we found earlier that X equals 1/2. Kramer also defined a Y matrix, abbreviated M with a little subscript Y. It's called the Y matrix because the X column is back, but now it's the Y column that gets replaced with the constants. So the X column comes first, where the Y column used to be is now the constants. So the X's are still 2, 3, 4. The constants are still 3, 2, 1. And Z is still 6, negative 5, negative 2. And you've probably guessed it, we need to find that determinant. I'm going to give you guys a couple of minutes to find that determinant. Okay, so going down, 2, 2, negative 2 is negative 8. 3, negative 5, 4 is negative 60. 6, 3, 1 is negative 18. That adds up to be negative 50. Going up, 4, 2, 6 is positive 48. 1, negative 5, negative 2 is a negative 10. Negative 2, 3, 3 is a negative 18. 48 plus negative 10, or 48 minus 10 minus 18 if you want to, is 20. So that gives us a negative 50 minus 20 is a negative 70. And you may have guessed it, Kramer says that the y value of our system of equations is the determinant of the y matrix divided by the determinant of the base matrix. So negative 70 divided by negative 210 is a positive 1/4, which was the y value. Well, you might be able to guess what comes next. It's the z matrix. What's that? Did I write that wrong? Yeah, that should be 1/3. You're correct. I was getting all excited. But yes, that should be 1/3. Thank you. Sorry about that. The Z matrix. In the Z matrix, abbreviated M with a little z by it, the x columns and the y columns are back. It's now the z column that's replaced with the constants. So x is 2, 3, 4. Y is 3, 4, negative 2. The c, the constants, is 3, 2, 1. Now, for the sake of time here, I'm going to let you find that determinant on your own. I will tell you that determinant should be negative 35. And Mr. Kramer says that the z value is the determinant of that z matrix divided by the determinant of that M matrix. Negative 35 over negative 210 gives us the 1/6 we're looking for. I used to do a considerable amount of computer programming for textbook publishers. I programmed the computerized test banks. What they did is they would randomly generate questions for tests, and then it would also provide the solutions for the instructor, for the teacher. It's capable, it's possible to program either method of finding the solution of a system of equations. You can program using that row echelon form, or you can program using these determinants. I always tended to program using the determinants just because it was easier for me to do. Either one is a lot of work. I'm not going to deny that. But at least the second one with the determinant breaks it up into smaller pieces, at least for me. When it comes to tests, in the homework at least, by the way, homework that matches up with today is homework 11B. It's going to ask you to do some of those row operations and stuff like that with those matrices. Or it's going to ask you which matrices are equivalent. So you'll need to be able to recognize which row operations have been done to show that it's equivalent. It will ask you to solve equations using matrices or solve systems of equations using matrices. Whichever method you use, whether you use the row operations from the book or if you use the Kramer's rule that I showed you, I'm okay with either one. I will get this video processed and posted for you as quickly as I can. And I'll see if I can find another video I have of Kramer's rule where I had more time to do more examples. And I'll post that along with it for you so that you have both of those videos to look at for Kramer's rule. Any questions? Okay, remember to also be working on those test corrections. You should have your tests back. If you don't, send me an email and I'll resend it to you. You can get up to half your points back on that test for doing those corrections. And also for extra credit, you can complete that study sheet for exam 2 and turn it in by next Tuesday. You guys have a great weekend. We'll see you next Monday.